To finish up this lesson on matrices, I would like to insist on their ability to act as gateways between spaces. So here I have the solar system, and let's say that this is our fixed reference. It's the solar system. So it's the world space. And so within the world space, we have other subcontext. So here in this case, we have Earth. And in it, there's a location for this bus. This bus is moving at a certain speed, with a certain direction, etc. Now, inside that bus, there are passengers, and those passengers occupy certain seats, and when some of them might move around. And so their movement and how they calculate their decisions is based on this context. They are not worried about their geolocation on Earth, but about their location in the bus and the obstacles inside the bus. Similar thing could be done with, say, a Mars vehicle or a big rover. And so this rover is in the context of, say, Mars. And so it has to navigate in this context. And so its position, rotation, and scaling are relative to Mars, the same way that the position, rotation, and scaling of the bus are relative to the Earth. Now, inside the rover or the vehicle, we have passengers, and those passengers, of course, they have to occupy some positions. They have to move inside of the vehicle. And so for them, their movements, the decisions they have to do is within a specific context, in this case, the rover. And so we can see how local positions, position, rotation, and scaling can stack up and build up world positions and world orientations, etc. In this case, world matrices, right, up, forward, and world position. So since they stack up, we still can relate them to our fixed reference. In this case, let's say it's the solar system. So this bus has an orientation, has a forward, a right, and an up, and a world position relative to the solar system. And so let's say that I want, for some strange reason, of course, these are very unrelated, but of course here in the scene, all the time we want to relate things that are in different hierarchies. And so let's say I want to put the vertices in B in the context of D. So I want to look at how do the vertices of B look from the perspective of D. So let's say that I want to put this passenger in the context of the rover. And so I would multiply the position of this passenger by the context where it is. So in this case, the context is the bus. So I'm going to multiply it by the matrix of the bus. This will make that I will get the position of this passenger relative not to the bus, not to the Earth, but to the solar system. Now, to put this passenger world position, well, it's funny that I say world when it's about the solar system now, or global position relative to the rover, I have to do this. Say, it's a bit tricky. Okay, so to do this, what I have to do here is to multiply the passenger global position or world position or scene position by the inverse matrix of the rover. So by doing this, I'm going to look at this world position from the context, or using the basis vectors, or describing this position with the right, up, and forward of the rover. So let's look into something similar here in layout, just to finish that up. So here I have a local position, and what do I mean by local? Well, this position is relative to a specific context, and that context is this matrix M. So when I come here and I move the matrix around, rotate it, scale it, you can see that this position changes. And so while it is 1.5, 2, and 2.5, I see it change in the scene. So our scene, our world space is what we see in the viewport. And so I see that changing, even though the pose of L is still the same. So if I turn on here this switch called data, basically allows me to see that pose of L, 1.5, 2, and 2.5. And I can see that this magenta vector does not change even when I rotate the matrix. Right, so how do I find the position of L not in the context of M, but in the context of the world? So to do that, I'm going to multiply this position by its context. So I'm going to do L times M. And so basically what I want is this, L times M. And this will give me the vector that goes from the world, from the scene space, to the position of L in the world. If I turn on this switch called components, I can see the same position described by the two sets of basis vectors. I can see I hat, j hat, and k hat scaled and added together to arrive to that position. And I can also see right, up, and forward scaled and added together to arrive to that position. And even if let's say I change this up vector here, you can see that this also changes. And now I have a sheared matrix, and it as I change the up vector, I also change the component of this position. Now let's look at another example in which I have a position that is not local to a context, but is already in the world context. So I'm going to reset this. I'm going to reset these as well. I'm going to flip this switch from L to W. So I'm going to put it to the left. And now I have a position that is in the world. What I mean by that is that I have here this matrix, and when I move this matrix, you can see that the position stays with its tail in the world. So as I change this matrix, nothing happens. But let's say that I want to look at this position from the context of this matrix. So if my space is this matrix, what does this position look like? So basically what I want is a vector that goes from here to here. And the question is, how do I solve this? Well, this position is already in the world. So what I need to put this world position in the context of this matrix is to multiply this position by the inverse matrix. So if I come here and I switch on data, what you can see is that this little matrix here is basically the inverse version of M. And after I invert M, I basically do the same thing that I've done before. I multiply the position W by the matrix. And so this world position times the inverse matrix will give me this black vector. But this black vector is also, it's a position that is in the context of M. So if I want to look at the data, I should look at the inverse matrix and the position that goes from the origin to that calculated position. And so this is what this looks like. Even though, of course, in the 3D space, after everything is applied, it kind of looks like this black vector, but the data looks like this. So as I change this matrix, you can see that the black vector stays in place because, this is the world relationship that I want to have, so that doesn't change. But the data of that relationship, of course, is changing. And if I turn on the components, we can see the same position described with the two sets of basis vectors. So here is that position described in the world with I hat, j hat, and k hat. And here is the same position described with the components of the matrix. So if I change, say, this, or if I change, say, this, you can see how the description of that position changes. So by knowing how to go from a context to the world and from the world to the context, again, I can jump between any context, because if I'm able to relate to the fixed reference, I'm able to relate to any context. So I hope this makes all these things a bit more clear. And next, I'm going to look into normalization and fall offs.